Now let us try to understand the free body diagram. In short, it is called as FBD, free body diagram. Children, first thing we need to understand that no system, whether it is a natural or man-made, can exist by itself all alone. So a single body cannot be completed. But to make our accounts possible for the easy way of calculation, what we are doing is we are isolating the part of a body from the complete system and we are making some calculations based on that. Okay, so this isolating of the body with the rest of the complete system is a diagrammatical representation. We are taking that diagrammatical representation of the body is called as a free body diagram. To make you understand this in a clear way, first of all, let us try to consider a book. Consider a book lying on the table. Let us consider a book lying on the table. If you consider this book lying on the table, then we observe that the weight of the body, weight of the book, having some mass m, that is weight of the book mg, always acts downwards. Okay, and the balancing force of this weight must be acting upwards, which is called as a normal reaction force, whether it is represented as n or normal reaction force. Sometimes they are representing the same with n and few people may represent the same with r. Okay, upward force n is balanced by the downward force. So this complete book is indicated with a simple dot and the weight of the body mg acting downwards, whereas the normal reaction force acting upwards. So this representation of a body itself is called as a free body diagram. To make you understand in a better way, so I would like to consider one more example. So let us consider one more example, that two bodies of masses m1 and m2 are attached with the help of some string as shown in the figure. Let the mass of the first body be m1 and the mass of the second body be m2. So they are lying on this wedge, so making an angle alpha and beta respectively at the two corners. No doubt the tension in the string must be acting, and this tension in the string let us represent with some letter T. Okay, so as we consider a massless string, so hence the tension in the two strings maybe will be same. Two different directions are same. So it's very clear that when it is attached to a frictionless pulley, we have, and the angle here in this direction is given as alpha, we can consider that the weight of the block always acts downwards. Weight of the block m1 always acts downwards. And this weight is given by the total weight of the block will be acting vertically downwards, and it is given by m1g. Let us drop. So if this weight, the direction of weight is perpendicular to the base of this equilateral triangle, so let us drop one more perpendicular to this side. So as this first line is perpendicular to the base line, we drop one more perpendicular to this line attached to the pulley. So, and this is what we know. As the angle between these two lines is alpha, so no doubt the angle between the two perpendiculars will also be alpha. Perpendicular drawn to this and perpendicular drawn to this. So angle between them will also be alpha. Okay children? Well, so this m1g again resolved into two components. The horizontal component that is attached to this is given by m1g cos alpha, and the vertical component perpendicular to this is given by m1g sin alpha. So the weight is vertically downwards. If this angle is alpha, this must also be alpha because these two lines are perpendicular to these. The blue color lines are perpendicular to the yellow colored lines. If angle between these is alpha, this angle between them should also be alpha. The weight of the body is resolved into two components. The horizontal component attached to this is given by m1g cos alpha, and the vertical component is, that means perpendicular to this m1g cos alpha, is given by m1g sin alpha. Similarly, if you look at the other portion of this, no doubt the weight of the second body m2 must be acting vertically downwards. This is m2g, and clearly this violet color line is perpendicular to this yellow color line. So again, let us try to drop one more line perpendicular to this yellow line, and this will be in this direction. So for this is perpendicular. As the angle between these two lines is beta, the angle between the two perpendicular lines must also be beta. So now it is very clear that, children, this m1g can be resolved into two components. The horizontal component is given by m2g cos beta, and the vertical line, something like this, is given by m2g sin beta. This portion is clear, children. And if we suppose that the body is accelerating in some direction, let us suppose that something like this, if the body is pulled like this, then this body will be pulled upwards. In this case, again, this can be resolved into two components. The equation here, if you consider, it is given something like this, the free body diagram. This point mass is taken as m1, and in this direction the force acting is T. In this direction, downward direction, the force acting is given by m1g sin alpha, and as it is accelerating upwards, equation for this is given by upward force minus downward force equals to the net acceleration. That means T minus m1g sin alpha equals to m1a, equals to upward force, because it is accelerating upwards, upward force minus downward force is equals to net force. So more and more practice will give you the proper clarity, children. Just I am introducing how it is being resolved into. So this portion, this is the free body diagram of this complete figure. Similarly, if you consider the right portion of this, again, if you drop a free body diagram for that, this mass m2 is something like this. For this mass m2, as it is accelerating downwards, and the downward force is m2g sin beta, whereas the upward force, it is something like T, but it is accelerating in the downward direction. Hence the net force here, the downward force is larger when compared to the upward force. If you write the this is a free body diagram for this complete portion, and the equation for this is written as this, as it is moving downwards, this force is larger when compared to the upper force. Downward force is larger when compared to the upper force. So downward force, larger force, m2g sin beta, minus smaller force, that is T, must be equals to m2a. So based on that, we will be solving the further equation. So this is how a free body diagrams are represented for the given figure. Okay, children, let us try to consider a few more simple examples based on that. Example 1, on a horizontal friction, on a horizontal surface, let us try to consider a body of mass m, and some force F is applied on that. First of all, if it is clear that whenever the body of mass m is kept like this, no doubt its weight is acting downwards and the normal reaction force must be acting upwards. This part is clear. And what else is given means, here a force F is applied on the body. So here what are the three different forces acting? First one, the right side force F, downward force M, mg, and the upward force is given by A. So the free body diagram for this is given as, so this is mass M is indicated with a small dot, downward force mg, upward force n, and side force F, and the body is accelerating sideways. As the force is applied, the body is accelerating sideways. So based on that, let us try to, so this free body diagram is finished. So let us try to represent the equations. Clearly, if you observe that these two, the body is neither moving upwards nor downwards. That means the upward force is balanced by the downward force. That means N must be equals to mg. So very clear that the body is accelerating sideways. So and there is no opposing force because it is a frictionless surface we have considered. Okay. So if there is no contacting force, then only force that is acting in the right way direction is capital F. And because of this F, the body is being accelerated. Okay. Hence, and this F is given by F is equals to ma. And from this acceleration, A can be written as F by m. So this is one example we have considered. Similarly, let us consider one more example, children. So again, consider the same horizontal surface, smooth surface. Let us consider a horizontal smooth surface. If it happens to be rough surface, the conditions will be different because the frictional force comes into play. So I have considered again a smooth horizontal surface on which a body of mass m is replaced. Earlier, the force is acted along the surface, that is parallel to the surface. Now let us try, suppose that some force F is acting, making an angle theta with the horizontal, making an angle theta with the horizontal. So first of all, it's very clear that the downward force acting on this is mg and the upward force is normal reaction, and this normal reaction force balances the weight of the body and there is no vertical displacement. So whenever the body is pulled in this direction, whenever the body is pulled upwards, pulled up slantingly, making an angle theta with this, it's very clear that this force F is resolved into its component vectors. So this component vector is given by F cos theta. F resolved into two components, the horizontal component given by F cos theta and the vertical component given by F sin theta. So on this body, whenever a force is applied making an angle theta with the horizontal, it's very clear that upward direction, normal reaction as well as F sin theta, two forces are acting on the upward direction and only one force acting downward direction and another force acting in the sideward direction. So this body is different when compared to the second body. Let us try to draw the free body diagram for this. First of all, we need to consider a dot. This dot indicates a mass m and the forces acting on this are, one is mg downwards, normal reaction upwards, along with that what is the other upward force, children? F sin theta. So normal reaction force is also there and F sin theta is also acting upwards. Two forces in the upward direction. Okay. Whereas one force in the side direction, that is only F cos theta. So if you would like to represent the equations for this free body diagrams, then it would be something like this. How it is written, children? Downward force is balanced by the upward force. That means upward force is N plus F sin theta must be equals to downward force is mg. N plus F sin theta must be equals to mg, or N can be written as mg minus F sin theta. Earlier case N is simply equals to mg, but now N is equals to mg minus F sin theta. That means the normal reaction force is lesser when compared to the weight of the body. The reason why you feel, okay, that's it, N is equals to mg minus F sin theta. And the net sideward force, if you consider that, the total acceleration is produced because of the sideway force. What is the force that is acting in the right direction? That is only F cos theta. The body is accelerated in the sideways. So F cos theta must be equals to MA, or A can be written as F cos theta upon M. A is equals to F cos theta upon M. So this first condition is slightly different from the second condition, because in the first condition force is applied horizontally, whereas in the second condition the force is applied, pulling force is applied at an angle theta with the horizontal. I would like to go with the third example, similar to the second one. So for this, what we consider is, let us consider a smooth horizontal surface. On this smooth horizontal surface, let us consider a block of mass M, and before the block of mass M is pushed, earlier it is been pulled, now the block of mass is been pushed to the right side. This is pulled. So the point of application of force is at this point, whereas the point of in the front, whereas the point of application in the latter case is at the back side. So we are pushing it by the application of force in this direction, that is by making in this direction the force is being applied. Is that clear, children? So if the force is being applied in that direction, then what we observe is we are making an angle theta with the horizontal. Clear, children? Well, so suppose if this happens to be angle with the horizontal, some angle theta is being applied. So this is the direction of force. The direction of force is like this, F, and angle with the horizontal is theta. Here also the direction of force is F, the angle made by the horizontal is theta. The direction of force is F and the angle made with the horizontal is F. This F is again resolved into two components. So one is the horizontal component is given by F cos theta, because this is theta here, this F here will be horizontal component given by F cos theta, and the vertical component is given by perpendicular to this. Perpendicular to this is now downward direction. So here it is given by F sin theta. Is that clear, children? Apart from that, identify the forces that are acting. No doubt, the weight of the body mg is acting downwards and the normal reaction force is acting upwards. So if you draw the free body diagram for this picture, what we observe is the dot indicates the body mass m. So downward direction, how many forces are acting now? One is the weight of the body and the other is F sin theta. Earlier F sin theta was acting upwards, now F sin theta is acting downwards. Whereas the normal reaction is acting upwards and the pulling force is given by F cos theta. Okay. So based on that, let us try the equations. So first equation, what is that? Upward force must be balanced by the downward force. That is, upward force N is equals to downward force is mg plus F sin theta. Earlier case N was found to be mg minus F sin theta. Now the force normal reaction N is found to be mg plus F sin theta. And the latter case, pulling force is given by F cos theta is equals to net acceleration that has been produced, or the value of A is again found to be F cos theta upon M. Both cases the acceleration might be same because the application of force is same, but the thing is that the normal reaction force is varied in two cases. Okay, children. So based on that, let us try to move the motion of bodies in contact. The next case is all about the contacting bodies. This is the individual body we have discussed. Later on we shall discuss with the contacting bodies. Here we go.